Koley from BMS second year. He's interested in commuters and problems, and today he is going to talk on what's Shannon. Thank you. So today we'll be talking about Shannon Entropy. So Shannon Entropy was first introduced by Claude Shannon in his 1948 paper. Huh? Oh, fine. Hold up, please. Okay. Okay. So Shannon entropy was first introduced by Claude Shannon in his 1948 paper, The Mathematical Theory of Information Theory, and it was his master thesis. So that's some. So first we will start with the classic idea of entropy, which we all learned back in our 11th and 12th grade. So the very basic example that we used back then was that of the three states of matter. So in a solid state, the entropy is less, that is, the disorderedness is lesser. It is more in the liquid state and even greater in the gaseous state. But today we'll be talking about this entropy from an information theoretic point of view. So let's consider a coin. So if you toss a coin, what is the chance that you will get heads? Or rather, how surprised would you be if you get a heads? The answer would be a bit. And that is exactly what it is. You will get just one bit of information from this event. As you can encode this heads to be 0 and the tails to be 1 and just transmit the outcome using this one bit. Whereas if you, let's say, toss two coins, so for each of the cases, you can go about the outcomes and mark them with 2 bits. And that's the maximum number of bits you need to transmit that information. So now let's consider an event U, which has n many outcomes. And let's say that each of these outcomes are equally likely. So in this case, we can encode all of these n many outcomes using just log to n bits, which is can be also written as minus log to 1 by n. And this is exactly your entropy for this event U. So the entropy of U is minus log to 1 by n. And this entropy is denoted by h of U. But as we know that not all events have equally likely outcomes. So there can be cases where the outcomes are not equally likely. So what do we do in that? For our entropy simply becomes sigma I equals 1 to n pi log pi, where pi's are basically the probabilities of the ith outcome occurrence. So now we have a expression for our Shannon entropy. So, but any expression is useless to us unless we have a characterization for it. As without a characterization, we cannot apply it to any practical situations. So let's look at some characterizations. So let's start with the characterization given by the man himself, Shannon. So Shannon first asks to consider an event with n many outcomes where the probabilities of each outcome ranges from p1 to pn. And he gives the following criteria for this entropy. First, uh, AHN is continuous in P. If the second criteria is that if for all I, all the PIs are equal to P, then we have that the entropy is is a monotonically increasing function. And the third criteria is, let's say we have an event A. So if we can break this event A into two disjoint events, let's say we break A into two disjoint events, A1 and A2. So we can write the entropy of this A as the weighted sum of these two disjoint events. That is, we can write H of A to be the probability of A1 multiplied by the entropy of A1 plus the probability of A2 multiplied by the entropy of A2. Let us consider an example. The others are pretty obvious. So let us consider an example for this third. So let's say we have the set of outcomes for an event to be A, B, and C. So we can denote this event A here as uh, it has one third probability of A getting A as the outcome, one third for B, and one third for C. Now let us break this down into two disjoint events. So here we first break we call this the event A1, where in the event A1 we get A with probability 1 by 3, and we get outcome among B and C with probability 2 by 3. And the event A2 is basically what outcome we get among the B and C. So we consider the conditional probabilities here. So now you can see that this H of A is basically H of 1 by 3, comma 1 by 3, comma 1 by 3. And here you can write this as one third the entropy of A occurring, that is H of 1, plus two-third the entropy of this B or C occurring, that is H of half comma half. Oh, so now time for a theorem. So what Shannon said is that there is only one function that can satisfy all these criteria. He said that H must be of the form minus K sigma pi log pi, where K is a positive constant, to satisfy these three criteria. This can be proved simply. I will not give the proof here. You can check it out for yourself. So now moving on to another characterization, which we will be calling the surprise characterization. So what do we mean by surprise? Well, there is a characterization for surprise also, but before that, let's give an idea intuitively. What we mean by surprise is that how surprised would we be if an event occurs? Well, the answer to that would be that we will be more surprised if the event is less probable. So now let's give the characterization for the surprise. Well, surprise is a function here denoted by S, where S is a continuous from 0 to 1. Uh, so you can prove that fairly easily. To, let's say A in the sequence. Now we know that an plus 1 minus n by n plus 1 an. If this tends to 0, then this also implies that an plus 1 minus an tends to 0. Just keep the Stolz-Zara theorem and you can prove this. And second is a theorem by Ardosh, Katai and Mate, which states that let's say we have a function phi on natural numbers. So where A and B are also natural numbers. Uh, and if phi follows additivity, and also if limit n tends to infinity, phi of n plus, And the second property being that limit n tends to infinity, phi of n plus 1 minus phi of n. This is equal 0. If these two factors follow for the function phi, then phi has the expression k log n. Sorry, phi n has the expression k log n. Using these two factors, you can just prove that this is the only expression that follows the Furby-Blindstedt characterization. So now there are many more characterizations for uh, this Shannon entropy. Huh? No, okay. So into some interval a comma b. So phi n is k log n. Okay. So there are many other characterizations that we can see, but we will not be setting any more characterizations. I will name them if anybody is interested to look at them. There are the recursive characterization, the categorical characterization, the Bradley characterization, which uses the idea of operators and simplicial complexes, and then there's the Baudot-Benequin characterization, which uses the idea of cohomology proofs. So moving on, we would like to have an application for this Shannon entropy. Now, Shannon entropy finds its applications in many fields. For example, data compression, then communication systems, and cryptography as well. So we cannot consider too many examples as this is a very short talk. So I will be considering the example for data compression. So first of all, the need for data compression is basically that we need to be efficient in storage and efficient about the transmission. Like every channel through which data is transmitted has a capacity C, where C is basically the bits per second that we can transmit through that channel. Now, how do we compress data? Consider this that we have some symbols which we need to transmit. Let's say S1 through S4. So we assign distinct. Now let's assign 0, 1 to 1, 0 to this, 0 to this, and 1, 1 to this. Now consider the code word 0, 1, 1, 0. Let's say we transmit this. Now on the receiver's end, the receiver does not really know now that whether we wanted to transmit the message S2, S3 or S1, S4, S1. This is the problem that arises with variable length code. The second would be, or the second desirable property is the code being instantaneous or prefix free. So what does instantaneous mean? Well, an instantaneous code basically means that whenever we get the entire code word, we can instantly get back the symbol. We do not need to wait for the code words for the other symbols to come through. Let's consider the same example again, but with different code words now. Let's assign 0 to S1, 0, 1 to S2, 0, 1, 1 to S3, and 1, 1, 1 to S4. Now, let's say we have this code word transmitted to the receiver. Okay, so there had been some technical issues for which I need to go back a bit. So please bear with me, the offline audience. This is for the online ones. So I will go back to this decodability part, which was the issue with the variable length coding. So we were assigning different code words to each of these symbols. Now, what I said was that if this is transmitted to the receiver end, the receiver can interpret this as S2, S3 or S1, S4, S1, any of this. And the second one was instantaneous or prefix free code, which is desirable to us. And instantaneous code is Basically, when the receiver the string of code words, you can instantly get the symbol as soon as the code word for that symbol ends. Let's consider this example where we have assigned the code words for each of these symbols. So let's say that this code word can think that the first code word can be S1, S2, or S3, any of these. But he can always get what the first code word is by counting back from the last one, as we know that there is a chain of S4s here. So last one, we can figure out the number of S4s and thus get the first symbol here. So to resolve this, Huffman came up with a coding algorithm using the source coding theorem given by Shannon in 1948. It states that for any string of symbol, there exists a string of code words such that the average bit length for that string of the entropy for them. Now coming to the Huffman coding algorithm, it basically assumes that the probability of the occurrence of each symbol is known. Yeah. Average bit length can anyway be increased, right? Just by putting zeros and ones. Yes. So once it's not clear that there is an existence of a string of code words, satisfying this inequality potentially equal to this. This is actually non-trivial. The just Shannon just included this in his long master's thesis, which he wrote as the mathematical theory of information. Yeah, yeah, it is greater than equals. Yeah. Oh, okay. Sorry. Then I'll write for all string of code words such that. Yeah. Sorry, mate. Okay. So the Huffman coding algorithm, we take all the symbols according to the decreasing probability of occurrence, and take the two with the until we get the entire set. We continue this process. And then we start from the root node and come down to the symbol and assign the values on the path as the code word for each of these symbols. So this is the code word that we are getting for each of these symbols in this particular example. Now here the entropy and the average bit length are equal, but there are cases where they may not be equal. I'll consider such an example. So let's consider 8 symbols. So let's consider this. So here the Huffman coding tree would look like. Set with the
for all of these. And when you calculate the entropy, you will get this to be approximately equal to 0.27. You can do the calculations by yourself. The average bit length, if you compute it, would be 0.279. This is an example where the average bit length is greater than the entropy. Now there exists a very interesting bound for this Huffman code, the average bit length that we get from this Huffman coding tree. I will not prove this bound, but rather just state it. So the average bit length from the Huffman coding algorithm we can see.
How can the bit length be less than 1?
Mind that again. Thank you, sir. So this average bit length from the Huffman coding algorithm will always be less than 8. The entropy plus 1 and will be greater than equals the entropy. This is not very obvious, and this is a proof which is not short enough to include in this talk. So I will urge you that if you are interested, you can check this out. And the second part that I would like to mention is the time complexity for this Huffman coding algorithm. No relation to Shannon, but still I like to state this further. So this comes about 3 months. So these are 2 facts that I found very interesting about the Huffman coding algorithm. And that's all for me. Thank you, Hrishik, for this wonderful talk. Do audience have any question?
What does HC resonance plus 1 mean? What do you mean by that?
HC, I noticed the Huffman coding algorithm is HC. I don't want to write the entire thing.
So is the Huffman coding algorithm gets us close to the lower bound, which is the entropy. Is it the optimum, or do we know, or something?
I mean, this is the best bound that is known till now.
Okay. So, but we haven't. But is it known that that gives the best possible average bit length, or something like that? Okay.
Best of my knowledge, you can do better. Best of my knowledge, you can do block Huffman codes and things like that. Like you can separate the symbols into 2 different blocks under some conditions, do Huffman code on each block. So that can end up giving better results.
For Huffman coding, this is the best.
Yeah, Huffman coding.
Huffman coding, you at most need 1 extra bit. So I got it.
Any more question? Okay, let's thank the speaker again.